I was like at the point where I did it.
All right, let's continue on with our discussion of acids and bases. And as I will, this lecture, next one, just to remind you, what is an acid? An acid is a proton donor. Proton means H+. So if I'm an acid, I'm going to give up my proton to you. And if I'm a strong acid, I'm going to give it to you whether you want it or not. Take it. And then the other side of that is a base. Under Braun-Sedlori's theory of acids and bases, which is still in use today, and the most widely used theory for acids and bases. And that is, a base is a proton acceptor. If I'm a base, I'm going around saying, hey, I want your proton, give it to me because I accept it. If I'm a strong base, I'm going to say, I'm going to just take your proton whether you like it or not. And we talked a little about strong acids and bases, but the switch was off for those. And talked about in water, the hydronium ion, H+, immediately reacts with water to give what's called the hydronium ion. I think I messed the proton reacts with water to give the hydronium ion, H3O+. And this turns out to be a very, very important species or chemical. Talked about conjugate acids and bases. Did that already. Talked about strings. And this is where I left off. Now, it turns out water is the most amazing compound. It keeps us alive, and it does a lot of other things that help promote life on this planet. And one of the most important things water can do with itself is react with itself. Now, this is called equilibrium. Unfortunately, in this class, they don't have in the active course file where I teach equilibrium. Equilibrium is when you have two opposing reactions. You see that by a double-headed arrow. And water can react with itself in an equilibrium to form a hydronium ion concentration compound and hydroxide. And notice the charges cancel each other out, and they exist together, so there's the net zero charge. But if you notice, one arrow is tiny and the other one is big. And that's because the rate, how fast it goes to this much or this way, or the completion, it mostly stays over here. But a small amount reacts, and that turns out to be extremely important for life on this planet. And some of the, how should I say, wonders of water. Now, it turns out when you have an equilibrium constant, I thought I shut that off. Hold on 1 second. There we go. When you have an equilibrium, they have a constant, which is based on concentration. And for water, the equilibrium constant, K, is used in chemistry for constant. W, water, actually it's named after me, KW. It was well in effect before I was ever born. And this is called the ionization constant for water. And it's equal to the molar concentration of H3O, hydronium, times the molar concentration of hydroxide anion. And this is for 25 degrees, which is room temperature, which is where we mostly deal with. And this is equal to 1 or 1.0 times 10 to the minus 14. And this is very important. First of all, let me, because I haven't talked about it here, so used to writing for this class. When you see something in brackets like that in chemistry, where X is a chemical formula, that tells you molar concentration. And in this case, that in every case, it's moles, X moles of whatever X is, actually, and per 1,000 milliliters or 1 liter. So when you see this, this tells you the concentration of the hydronium ion concentration times the hydroxide equals water 1.0 times 10 to the minus 14. And in keeping with my new policy I started last spring, in the past I had asked you to memorize this. Now I've changed, you know how to use this. And yes, you should. This is probably one of the most important things I'll teach you this semester, and what we'll be getting into in a little while. So what does that mean? Let's see if I have it on the next slide. Nope. Let's do a couple things. Let's look at the following question. Now, I'm not putting points up here because this question will be part of another question that I'll deal with probably this morning. And let's take a look at this. If the hydronium ion concentration, and I could put it like this, is equal to 1.0 times 10 to the minus 5th, what is the hydroxide? So what are we trying to find? What are we given? And as soon as you see this and this, what else do you know? You know that the water ionization constant, Kw, which I'll give to you on a test, is equal to the hydronium ion times the hydroxide ion concentration, and that's equal to 1.0 times 10 to the minus 14. So, I know this. What do I want to solve for? The hydroxide. So I want this alone on one side. What do I do to get rid of that? Divide by it. And whatever I do to one side, I have to do to the other. And this cancels out. This leaves me with hydroxide equals 1.0 times 10 to the minus 14 divided by hydronium ion concentration. And now I can put in my numbers because I know what this is. So this is now equal to 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 5. I don't need a calculator. Oh, quick thing for people who didn't grow up at calculator time, which I didn't. When I was in school, you didn't have a slide rule. But since you all have a calculator, you don't need to know this, but I thought I'd throw it in free of charge on this cold morning. And so if I do the math here, 1 divided by 1 is 1.0, and this would be 10 to the minus 9. And that's how you do it. And the key thing to know is that the ionization constant, Kw, not named after me, but I like to believe it was, is equal to the hydronium ion concentration times the hydroxide, which is equal to 1.0 times 10 to the minus 14. Oh, that was fun. Let's do another one. Everybody have this copy down that one? Do you have this part? Okay. While you're doing that, I'm going to have some water, which is undergoing that equilibrium right now before your eyes. Oh, tonight at midnight, I'll be giving speed note-taking lessons. No. When you're done copying, look up. Okay? All right, well, one or two you're finishing up. I'll start on the next problem, and this way you have time to copy that down. Now, why don't you try this one first? If the hydroxide ion concentration is 1.0 times 10 to the minus 4, what is the hydronium ion concentration? Catalog? Joe. Remember, when you're done, you can look up and smile or frown. It's a free country, at least so far. By the way, today is a historic day, what's happening in Washington. I've lived through this once before with Nixon, and it's amazing what the country is going through, which it shouldn't. But that's my personal opinion. I should be in the classroom. And it will, sort of. All right. Looks like everybody's just about done. Let's take a look at this. And the question is, what are you trying to find? And that is the hydronium ion concentration. What are you given? The hydroxide concentration. But you also know this. Kw, not named after me, but I like to think so, is equal to the hydronium ion concentration times the hydroxide, which is equal to 1.0, I have there's 1, times 10 to the minus 14. And that will be given to you. And now, therefore, I know to start with this. And what am I trying to solve for? Well, I took the time to say this. The hydronium ion concentration, H3O+. So therefore, I want to get rid of hydroxide. How do I get rid of hydroxide? I divide that, because anything divided by itself becomes the number 1. Essentially, it's gone. Well, whatever I do to one side, I have to do to the other. So I will. Anything divided by itself becomes 1 times anything is that anything, in this case, hydronium ion concentration. And now it's equal to this. And I know what the hydroxide is, so I can put that in. Do the math, I can do this in my head, and you get, and that's how you do it. You got this all written down. Okay, everybody got it written down? What? And therefore, knowing Kw, which, one sec, which you don't have to memorize, but know that it's there and you should use it, helps you solve these questions.
So would the answer just be the numbers, or would you have to
Well,
add on like H3 plus?
Technically, you could put moles per liter, but just put a number there. I have never, ever, ever, one more, ever, taken off points on a test if somebody doesn't put down the units. They show me they can do that. When I grade, I'm not grading to say, ooh, how many points can I take off a student? No, oh, it's right, good. I'm not going to be nitpicking. I've never nitpicked ever. Where did you find a nitpick? Never mind. All right, now, let's move on. How many of you have ever heard the term acidic, basic, or neutral? Those of you who don't want to raise your hand now. No. Anyways, how many of you have heard inside your stomach, the fluids in there are acidic? And I think most of you, if you had any health courses or learned about your stomach, that's acidic. And certain drain cleaner is basic. And certain things are called neutral. Well, where do we get this? And this is where, when we're talking about this, we're talking mainly about aqueous solutions. Aqueous meaning you're in water. And water reacts with itself to form hydroxide and hydronium ion. And acidic solution, you should know this. If you have an acidic solution, the concentration of the hydronium ion concentration is higher or greater than the hydroxide. And here's a simpler way to write that. Which tells you, is everybody familiar with the greater than symbol in math? And this tells you when you have an acidic solution, the hydronium ion concentration is greater than the hydroxide. And if this weekend, if you go to a party, or in a couple weeks you go to a Thanksgiving dinner, which I hope you all do, you can astound all the people at that dinner or party and say, do you know your stomach is acidic because the hydronium ion concentration is greater than the hydroxide? Don't. You'll lose friends real quick. But it is true. Your stomach is acidic because the amount of H3O plus in my stomach is greater than the amount of hydroxide. By the way, it's not just mine, it's yours too. Now, the next thing is a basic solution. And a basic solution is the hydroxide concentration, OH minus, is greater than the hydronium ion concentration, H3O plus. I tell you, the closer we get to Thanksgiving, the worse my brackets look. It's true. But anyways, for a basic solution, hydroxide ion concentration is greater than hydronium ion concentration. And we sometimes call this an alkaline solution. How many of you ever heard of the alkaline batteries or alkaline? And that's because initially batteries had acid in them, and then they found they could make better batteries that lasted longer, like the Energizer Bunny, and I just pulled a commercial out of TV. And I don't use those, I use different ones, but anyways, their commercials are nice. There, they found when they used the base where the hydroxide is greater than the hydronium, you get a battery that lasted longer, was smaller, and cheaper. And that's why they're called alkaline batteries. Now, there's a third designation when we're talking about acids and bases. And that's a neutral solution. And a neutral solution is when the hydronium ion concentration is equal to the hydroxide. So acidic, you have the hydronium ion concentration greater than the hydroxide. Basic, you have the hydroxide greater than the hydronium. And then when they're equal, we call that neutral. Let's assume I was able to find out in the solution that the hydronium ion concentration was 1.0 times 10 to the minus 10th. I wanted to know, is that acidic, basic, or neutral? And I said, well, I've got to go now calculate the hydroxide. And if I did, I can do the speed because I know how to do it fast. It would be equal to 1.0 times 10 to the minus 4th. And now I can look and I think, and I said, well, this is greater than that. This is a basic solution. But that's a lot of work. I tell you, chemists, especially organic chemists, are lazy. When there's an easier way out or a better way out, chemists usually find it, which is a good thing. And they did in this case. And what came up was called the pH constant. And of all the things I'm going to teach you, this is probably one of the most important things for your daily life and out after this class, and that's the pH constant. pH is a scale. It's a small scale of numbers that is used to specify the molar hydronium ion concentration in an aqueous solution. And this will be given to you, but you have to know how to use it. And by the way, if I have a dial on how important this is and it goes up to 10, I've just turned it up to 100. By definition, pH is equal to minus the log of the hydronium ion concentration. Now, it's time for a holiday gift from Dr. White. How many of you are familiar with how to calculate logarithms on a calculator? One or two. Most of you are. So I'm going to give a gift to you. Let's look at the following. Let's look at the following. The question is, what's the pH of a solution with the hydronium ion concentration equal to 1.0 times 10 to the minus fifth? We get a new pen out. So what are we trying to find? pH. What are we given? That. What do we also know? We also know that pH equal minus the log of the hydronium ion concentration. So now I know that pH equals minus the log of the hydronium ion concentration. In this case, what is the hydronium ion concentration? 1.0 times 10 to the minus fifth. And now, here's my gift to you. If this were another number besides 1 or 1.0, then you'd have to take out your calculator, for those of you who still have one, your slide rule, and do logarithm, and then take minus of that. Well, no, I'm going to make it easier. If the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. And that's the way logarithms go. Logarithms, I went to Technical Institute and took math through partial differential equations. But this is my gift to you. If we look at this, what's x? 5. Therefore, immediately you know the pH is 5. And that's my gift to you. Otherwise, take out your calculator, find your logarithm function, put that number in, and then after you get that number, multiply it by minus 1, and that would be the answer. You'll get the same thing, I guarantee. Better yet, I'll bet on it. And when I say I'll bet on anything, I already know I won. So never bet with me. And why don't you try this one? Everybody got that written down already? Why don't you try this one on your own? What is the pH of a solution if the hydronium ion concentration is 1.0 times 10 to the minus 10? Well, one thing, someone told me the other day that they were having trouble way back seeing the board with my videos. 2 weeks ago, I learned with the software I used to process it, how to brighten it up, so you should be able to see the board in the last 5 or 6 videos, maybe even more. And I'll go back after the semester. I don't have time now to correct the other ones. So I'll be teaching this again next semester. Those that don't know, try Google. I'm glad Google's around. I like it better than Bing. Or is Yahoo still up and running? I haven't used that in eons. I think everybody's just about done. Let's take a look at this. What are we trying to find? What are we given? What do we know? The pH equals minus the log of the hydronium ion concentration. Therefore, to find pH of a solution, I know the hydronium ion concentration. I know that. I know what it is, because I wrote it right here. So this is minus the log 1.0 times 10 to the minus 10. And my gift to you is, if the hydronium ion concentration is 1.0 times 10 to the minus x, the pH is equal to x, and I can immediately say it's 10. And that's how you do pH. And the question is, so what? Why do I want to learn pH? Well, it's important. It says it on this slide. And let me show you why I put that down. One of these days I'll put this on the slide, but for now, I'll use the old-fashioned way. pH, it can only go from 0 to 14. It can never be less than 0. It can never be more than 14. If it is, you made a mistake. Which reminds me of a story years ago. I was managing this research group. I had about 15 people, PhDs and master's degree chemists at this one company. And someone gave me a report. It was a master's degree chemist. And I looked at the report, and because I had to sign off on it, literally I had to write my signature before it was released to the company. That was part of my job. And I looked at the report, and the person had pHs for certain solutions of 15 and 16. And I called them back into my office after I read the report, and the part of Dr. White you don't know is the manager when he gets mad. And I called him in, he sat down in my office, and I said, point blank, do you want to keep working here? And he got really nervous and said, what's wrong? I said, well, he gave me a report. You have in here pHs of 15 and 16. Any undergraduate chemistry major knows pH can't be back higher than 14. I would suggest you go back and measure these again and recalibrate. There's an instrument called a pH meter. If you don't calibrate it properly, you can get bad numbers, but you should know if it's over 14, it's bad. Something's going wrong. And he did. He corrected them, and he never did that again. But pH can never be lower than 0, higher than 14. Now, when pH is less than 7, we call that solution acidic, which you learned about, but this is easier to see. When pH is less than 7, you immediately know that solution is acidic. Oh, by the way, sometimes on cold weather, Dr. White gets very slow. Everybody get the message? All right, when pH is less than 7, you have acidic. When pH is equal to 7, it's called a neutral solution. When pH is above 7, we call that basic. And that's the beauty, and it is beautiful. Now you know, our chemists, when I think this is beautiful, which it is, that pH is very useful. Now, important thing to remember is pH is a logarithmic scale. For those who aren't familiar with logarithmic, each change in one number is a power of 10 difference in the concentration of the hydronium. So even though pH 7 and 6, they're only 1 unit apart, they're actually a power of 10 apart when you talk about concentration. And that reminds me that I do have time. My last patent, when you file a patent, the government has people who review it to make sure this hasn't been done before and hasn't been mentioned in somebody else's patent, because then it's not original. And the examiner, who was obviously new, wrote back to our lawyers, we're going to deny this patent because in your claim the pH range for a certain series of products was 9.5 to 14. And someone else claimed something similar, which it really wasn't, at a pH of 7.5. And you're at 9.5, and that's pretty close, and we're not going to allow it. Unfortunately, I had to teach the lawyer for our company pHs. I said, that's power of 100 difference, 2 almost, and those are different ones. Well, he went to that person, no, they're similar. And I had to push on our lawyer and say, do you want me to come with you to Washington? Go to this person's manager and have them contact me. And I talked to the manager at the patent office. And, I don't know. And I said, hold on, I'll prove it. So I went back to the lab. I was already manager. I had people go to the lab and run the same reaction at pH 7 and pH 9.5. It didn't work at pH 7 or 7.5. It worked properly at 9.5. And I had that written up, and I signed it off, and had it all notarized because it's for legal. And then it was sort of like beating someone over the head with a baseball bat. Look, here's the evidence. I told you it was true. Now you know it's true. And then it was issued. But it was sort of frustrating that someone in a patent office didn't know the difference that pH is factors of 10, even though you look, it's only 1 or 2 numbers different. No, it's a factor of 100. Anyways, this is a pH scale. Why learn it? How does it help you? Let's go out into the real world. That's the fun part about chemistry. You got a teacher knows the internet. in Wikipedia. Let's look at this interesting scale. Now, here we have the pH, and notice it goes from 0 to 14. Now, what are some common things? First of all, your blood is very close to neutral. If it goes outside a certain range, guess what? You're dead. And Mother Nature found a way, which I don't teach in here, it's called the Chandler's Principle, to keep your blood, other than when something really dramatic happens to your body, in that narrow range, very narrow range. And in fact, there's a great movie, and the first one, not the second one stunk, called Andromeda Strain, which dealt with how a microbe from outer space, which was killing people, that in certain instances, the blood, when it was at a certain pH, would kill that microbe. I just gave away the movie, but I don't know, just forget I said that if you're going to watch it. But it's called Andromeda Strain, and it's a great movie. And if we look at a couple other things, let's look at a lemon. How many of you have ever bitten into a lemon? And it's pretty sour. You go, ooh, that's sour, if you've ever had real strong lemonade. And that's because the pH is low. When pH is low with certain things, when they're acidic, Mother Nature has given us the ability to say, ooh, that's something different, it's sour. It's sour, not solid, it's sour. And your tongue tells your brain, ooh, that's sour, and that's because it's acidic. And lemons are very acidic. Now, how many of you have ever bitten into lime or put lime around your shot glass? Don't do that. But anyways, limes are also sour, but not as sour because they're not as acidic. They have a higher pH, but it's still less than 7. Now, if we go to the other side, ammonia cleaner is very acidic, basic. And you see the pH is above 7, and it's a very strong base. And bleaches are bases also. And they don't have it up here, but if you make a strong solution of sodium hydroxide, the pH is anywhere from 12 to 14. If you make a strong solution of hydrochloric acid, like in battery acid, your pH is going to be close to 0. And pH plays an important role. How many of you have ever taken care of a swimming pool? I had one in my backyard, came with the house until I got rid of it, thank God. In Chicago, it's sort of not too good to have a swimming pool because you don't have that many days you can use it because of the weather. But one of the important things when you're taking care of a swimming pool is the pH of the water. You want to keep it slightly basic, just above 7, because if it's too acidic, your eyes start telling you, that hurts, and you get bloodshot red eyes. And if it's too basic, same thing, it'll affect your skin. How many of you are familiar with personal care items like hand lotions and cosmetics? And there, do you want to put something on that when you put it on your hands, make it soft, the skin, why is my skin turning red? Well, that's because it's either too acidic or basic. And companies that make those type of products keep the pH near 7 so it doesn't irritate your skin. Or if it's a shampoo, it doesn't irritate your scalp, and all things like that. And one of the things you don't know, but I do, is just about anything you buy, personal care, one of the important specification is before they ship it or sell it to people, they measure it, is pH. Because you want it around 7 or you're going to get a lot of lawsuits, which is not good, and lose a lot of customers. thought I had it. Let's try this. No, I can't find it easily. All right, let's just look right up here. Your stomach, I said it was acidic. How do I know that? Because the pH is way below 7. And on this one, I don't know if it's true or not, but let's assume it is for the time being, pH of your stomach can range from 1.5 to 3.5. And why is it acidic? Because one of the miracles of life for me personally is I have in my stomach, and you do too, cells that make hydrochloric acid, HCl, and put it into your stomach. And you put an acid in water, the pH is going to go down. And it's going to become acidic. And that helps break down your food. That's the first step Mother Nature uses to break down your carbohydrates, your proteins, and your fats and oils, the molecules that your body now uses to do whatever it uses for. Did I tell you last time I took biology, was freshman year of high school? Not that there's anything wrong with biology, but by then I knew I wanted to be a chemist. I don't get any kickbacks from Home Depot or this company, but I'll tell a nice little story. And the offshoot of the moral of the story is, even with a PhD in synthetic organic chemistry, don't argue chemistry with people who work at Home Depot. It's a losing cause. All right, when I bought the house a long time ago I'm living in now, and I moved in, after a couple weeks, my kitchen drain stopped up. And I said, oh, the previous owner, his wife, put grease down there and it solidified and stopped up my drain. So since I was in a new house, I figured, all right, I'm going to get the Roto-Rooter. I think I might have told the story, but I tell about but now you'll understand the aspect of it. And I got the Roto-Rooter guy out. He did it and unclogged it and put the Roto-Rooter thing in there. And then about a week or two later, it clogged up again. And I said, all right. And I called this guy because I had a guarantee. He came out, did it a second time. About a week or two later, did it again. And I'm upset because I'm wasting time, not the money that I paid him. And he came out, did that, and took a bottle of stuff and said, this is going to keep it clean. And I said, can I look at the bottle? And being an organic chemist, I knew exactly when I read the ingredients, oh, that ain't too much good. But I let him do that. And about a week later, it clogged up again. I said, well, I'm not going to waste my time. I went to Home Depot, and Home Depot, about 2/3 of that wall was bottles of different drain cleaners. I picked up a couple. I think you're familiar with like Drano and all that. I looked at the labels, and they all had hydrochloric acid in them, which means it's acidic. Now, what does that mean? That means we've got an acid present. And I'm looking which is the best one, being somewhat of a good problem solver. One of their workers came over who worked in that area and said, can I help you? And being a clever person I sometimes am, sometimes I'm not, I asked him, all these, which ones did a plumber's use? Without even thinking, he said, that one, that one. I picked up the bottle, and if you look at the back, it says sodium and potassium hydroxide. Let's see if they have a label here. Well, here it says in the guide, non-acid formula. Well, it's got base in there, and I don't see the label here. Oh, wait. Everybody bring out their now, we can't scroll. and you can't see it, but it says on there sodium and potassium hydroxide. And I look at that, and being a chemist who knows sodium and potassium hydroxide are bases, I said, oh, this is a base, those are acids, that's why it's different. And he immediately said, no, that's an acid too. I said, no, the pH of this is going to be higher than 7 because there are bases in there. He said, no, it's an acid. At that point, I realized he'd helped me point out a good product. I said, okay, thank you, and I walked away. But it was a base, and this stuff works real good. Now that you know about this, let's do the following. And let's look at the following hint. What is the pH of a solution if the hydroxide ion concentration is 1.0 times 10 to the minus 6? Good question. So what are we trying to find? pH. What are we given? The hydroxide ion concentration is that. What else are we given? We know pH equals minus the log of the hydronium ion concentration. Wait a second. I don't have the hydronium ion concentration. But what else do you know? You know that the hydronium times the hydroxide ion concentration equals 1.0 times 10 to the minus 14. So now you have to do this in 2 steps. First step is you have to determine or find hydronium ion concentration. And how do we do that? We know that Kw, which is the, oh, I love that. I was meant to be a chemist. Things were already named after me before I was born. But anyways, hydronium ion concentration times hydroxide equals that. We want to solve for hydronium so we can determine the pH in the second step. So how do we get rid of hydroxide? Divide by it. Whatever you do to one side, you have to do to the other, which I have done. Now, this cancels out. I'm left with the hydronium ion concentration equals 1.0 times 10 to the minus 14 divided by the hydroxide concentration, and that is 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 6. And if you take out your calculator, you'll get 1.0 times 10 to the minus 8. Am I done? No. I'm trying to find pH. Is everybody with me how I got that far? step number 2, you'll find the pH. And what do we know? pH equals minus the log of the hydronium ion concentration. In this case, it's 1.0 times 10 to the minus 8. And remember my gift to you, a nice gift, made your life a little bit easier, just a little, is if the hydronium ion concentration is this, 10 to the minus x, 1.0 times 10 to the minus x, the pH is x, therefore this is 8. Now, the next question I could ask you, part B, is that solution acidic, neutral, or basic? And, in case you forgot, I didn't. We now know pH 8 greater than 7, this is a basic solution. So the key thing here is, first of all, if you're not given the hydronium ion concentration, you're given this, you have to solve for that using the fact that Kw is equal to hydronium times hydroxide concentrations times 1.0 times 10 to the minus 14. Ooh, another gift that started last spring. In the past, I'd make students remember this. I'll give this to you as important information, so you don't have to memorize it, but you do know how to use it. I want to solve for this hydronium to use it in pH, so I'll divide by hydroxide, and I'll do the math, and now I have this, so I can figure out the pH in the second step by putting it in here. And my gift to you is when this is 1.0, and my test and final always will be, int, and it's 8. Everybody have this while you're writing? I'll let you go ahead and let's do it. Let you do one on your own. What is the pH of a solution if the hydroxide ion concentration is 1.0 times 10 to the minus 10? We're into pH practice time. Have a chance today or tomorrow when you're at home, think about some of the things you use in your daily life, maybe things you eat and other things, and think about, are they acidic, basic, or neutral, and look on the internet and you'll be able to find it out. time flies when you're having fun with pH. All right, let's do this. And what are we trying, first of all, let me clean off the board. What are we trying to find? pH. What are we given? Hydroxide equals concentration equals this number, 1.0 times 10 to the minus 10. We know that pH equals minus the log of the hydronium ion concentration, which we're not given, but you also know that the hydronium ion concentration times the hydroxide ion concentration equals 1.0 times 10 to the minus 14. So we have to do two steps. You have to find the hydronium ion concentration, and you do that by using this. To get rid of the hydroxide, I'll divide both sides by that. This becomes 1. Anything divided by itself is 1. And I now know that this hydronium ion concentration is equal to 1.0 times 10 to the minus 14 divided by the hydroxide, which I just happen to have here. And I'll put that in. I do the math, which I know how to do in my head, and now I'll do step number 2. And to calculate the pH, I know that, oh, it's even on the screen there, it's minus the log of the hydronium ion concentration. And what is that? Well, I figured it out right here. And my gift to you is that this is 1.0, and always will, 1.0 times 10 to the minus x, where in this case x is 4, the pH will be x, in this case 4. Now, is that basic, acidic, or neutral? Oh look, someone put something nice on the board, and it's less than 7, so this is acidic. Now, one of the things I forgot to mention, let's go out in the real world. pH of ketchup is about 3.9. Why? It's acidic. If you go home, if you have a bottle of ketchup, if you don't, go to your local big box store, grocery store. They don't charge you if you pick up things and look at the labels. I do that all the time. They don't even get mad at you as long as you put it back where it came from. you'll see the first thing is there, vinegar. Let's find out if I can find one of those. And vinegar is a mixture of acetic acid and acid and water. And here we have Heinz. It's probably my favorite ketchup, even though I like barbecue sauce better. But if you look here, tomatoes and then vinegar. By the way, tomatoes contain a compound that's also acidic. Have you ever eaten spaghetti sauce or something, if you have a canker store, and all of a sudden, ooh, that made it hurt? That's because spaghetti sauce is acidic also, because tomatoes are acidic. Anyways, vinegar is an acid, and therefore, guess what? Ketchup is acidic, pH less than 7. Now, let's go to some of the other condiments you put on your hot dogs and hamburgers. And what's the next one? Mustard. And mustard is also acidic because it's made with vinegar. And let's go to the last one, if you're not the last, but important one, if you're from Chicagoland, which I am, and you've been eating hot dogs here all your life from the local stands, they put on relish. And relish here is, that atomic colored green that glows in the dark. Have you ever seen that bright green they put on good hot dogs? And relish is made with, guess what? Vinegar. And what else do you put on your hot dogs if you're from Chicago? Pickles. If you look in the pickle jar, you'll see that's made with vinegar. So all the things you put on your hot dogs and hamburgers make it more acidic. So next time you're at a picnic, you can point that out to people and lose friends. And based on the fact that you're rustling, I still have 2 minutes, so hang in there. And I can't think of anything basic, but generally things that make something sour are acidic. How many of you are familiar with in different cultures they have sweet and sour dishes? If you eat certain meatballs, they have sweet and sour meatballs. If you like Chinese food, which I do, you have sweet and sour pork. And they put in stuff there to make it more acidic, and that's how it gets the sour. And since you guys are all fidgeting, I don't want fidgeting students, I'm going to let you out a whole 30 seconds early. All right, be on time for lab.